Okay, so our lesson today is about 11.2 probability, and our objective is to find the probability of an event using theoretical, experimental, and simulation methods. So we're not going to work every single problem on this. I'm trying to streamline this chapter and get us through it quickly as possible so we can end our year going through most of the material. All right. So right now you should be passing forward 11.1. That was our homework. It was online and videos out there. You should also rip out 11.2 because that's what we're working on today. And it's very possible that we'll even get through our lesson before you walk out of here and be done with your homework. Then everybody's received a study guide for our Chapter 11, Part 1. This is in two parts. Part 1 is 11.1, 11.2, 11.3, and 11.4. Okay, so today for your bell work, I want you to work problems 1 through 4 on your study guide, which was directly like your lesson on Friday. Okay? Do not lose this. I will not have extras to give anybody. Okay? So I'm going to set the timer for like 3 minutes and then we'll begin. All right, timer started. Girls, get busy, please. You should be working on your work. And while you're doing this, I'm also going to remind you I'm staying tonight for makeup test. And let me pause because I don't want to put names on here. All right, so 1 hour after school today. I'll stay for makeup. And then after we get the 100-point test out of the way, then I'll focus on the larger quizzes. And when those are caught up, then I'll focus on the small quizzes. About 15 more seconds. Okay, so let's do a quick review of what we did last week. So last Friday, we introduced the chapter on statistics and probability. And Friday we talked about permutations and combinations. And I gave an example of how do I remember what's a permutation and what do I remember is a combination. Well, I think of permutation, it has the word mutation. And I think of the creature that dwells in the sewers that's been in the radioactive waste. And he starts as a normal person and then he gets in the radioactive waste and he changes from normal human being to getting blisters and sores, and then he starts turning into zombie skin and all gross, and then he turns green and his skin falls off and he gets big buggy eyes, and he just goes through these mutations in a specific order. So I remember permutations as being a specific order, right? Mutation happens in an order. Permutations, the order matters. In combination, the order doesn't matter. And we talked about two different formulas last week, the permutation and the combination. Before we did those, we just talked about one rule, and that was the fundamental counting principle. And we learned that if there are several different items, how many different ways can we present them? So, for example, in your homework, it said you must make a password for your email account. The password must consist of 2 letters followed by 4 digits. Well, we've got an alpha, and digit, 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 digit. Well, think of this. How many ways can we represent an alphabetic character? Well, there's 26 letters in an alphabet. So 26 possibilities for this first position, and that makes 26 for the second position. And how many digits can we display? Well, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different digits we can put there. And same for these positions. So when the fundamental counting principle says how many different ways, possibilities do we have for this password? Well, it's going to be 26 times 26 times 10 times 10 times 10 times 10. And we know that 26 times 26 is 676, and there's 1, 2, 3, 4 zeros after that, right? And then that comes out to 6,760,000. And we did that together in class, but that's just a quick reminder of the fundamental counting principle. We talked about the permutation, and I want you to get your yellow calculators, and I'm going to show you a couple of things. I'm going to show you how we did the formula, and I'm going to show you the shortcut on the calculator. So we learned that the permutation, that's one where the order matters. So I've got 15 students. How many different ways can they get first, second, and third place? Well, 15 is the total. That becomes your N. Here we go. So if I have 15 permutation, and we're going for first, second, and third place. So that's 3 ways to order that, right? So the order matters. So permutation, 15 total, we learned that that is N factorial over N minus R factorial. That's my N, that's my R, right? So this becomes 15 factorial over 15 minus 3, which is 12 factorial. Well, we also learned that there's ways to simplify this to save us time. And we know that 15 factorial is 15 times 14 times 13 times 12 all the way times 11, 10, 9, all the way to 1. Over, and we know 12 factorial times 11 times 10 all the way to 1. Well, these cancel out. The 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2 all the way to 1. Those cancel out. So we're left with 15 times 14 times 13, and that becomes your final answer. Well, let's see what that is. On 15 times 14 times 13 is 2730. All right, now let me show you how to use your calculator for permutations. So if you will hit clear, and I showed you how to clear your calculators last week, hold your on button and hit clear, and it will say memory cleared. So that way, if someone's been messing around with your calculator or changing settings, or they're putting stuff in memory and all of a sudden you don't understand how it's working, this will give you a fresh calculator every time. All right, now, so how do we do this with the calculator? Well, we worked it manually last week, but now I'm going to show you how to use the probability. So if you click your 15, press 15, the number 15. Now hit your probability button, and then you notice under probability we've got the first selection is in PR, the second selection is in CR, so there's your permutation combination, and the third one is our factorial. Well, we're doing permutation right now, so let's select 1. So I'm going to press enter. So now my screen looks like this, 15 in PR, and now there were 3 places, so I'm going to press 3 and press enter. And what did you get? 2,730, which is what I got manually. So that's how you work these on the yellow calculators. I love these little calculators. All right? Any questions? Now, of course, I want you to know how to do this without the calculator, because what if I said no calculators allowed on the test? But it's a wonderful way to check your work. I'm not saying I'm going to do that, but I might. I might do a quiz that way. All right, we talked about factorial also, like 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? But then I showed you on the calculator, let's hit clear, and you press 6 and then go to probability, cursor down twice, or select 3, the number 3, either one will take you there, where it says 3 factorial. That should be highlighted now, and press enter, and press enter one more time, and it will give you 720. So that's how you do your factorials on the calculator. So these are things we did last week, and then we worked 3, 4, 5 like that. So the last thing we worked was doing the combinations. There it is. So first we just evaluated each expression. And we knew when you talk about combinations where order doesn't matter, you've got more possibilities, right? Because if it's not going in a specific 1, 2, 3, 4 order, your possibilities are greater. So this is the one that's the larger number. So if we do the NCR, we're doing combinations where order doesn't matter. So that was on the back page of our assignment, and it said at first we just had like 6 problems evaluating. So they gave us like a 7C2, right? So we know that that's going to be equal to n factorial over r factorial times n minus r factorial. So this would be equal to 7 factorial over 2 factorial times 7 minus 2, which is 5 factorial. Well, this one would be quite simple to do by hand. So we know 7 factorial is 7 times 6 times 5 factorial. Notice that I'm just going to my largest factorial that I want to clear. Right? And these 5 factorials cancel out because it's 5 times 4 times 3 times 2 times 1 and 5 times 4 times 3 times 2 times 1. All of that cancels out. So I'm not even going to write it out. And now I'm left with 7 times 6, that's times, over 2 times 1. Well, again, I can clear this out. Well, 2 times 1 is just 2. And 2 goes into 6 3 times and into itself 1 time. So I'm left now with 7 times 3 over 1, which is just 21. And that's your answer. We have 21 different ways to represent that. Now, let's plug this into the calculator using the C, the combination function. So hit clear and go to 7, probability, and now cursor down to number 2, press enter, that's the NCR, should show on your screen, and now type 2 and enter, and you should get 21. Okay, any questions about that? So that's everything we did. And then we learned how to tell the difference between a permutation and a combination. It's like when order matters. On our homework, it said an ice cream parlor offers 14 different types of ice cream. And how many different ways can you select 5 types of ice creams to sample? So they're saying out of 14, how many ways can I pick 5 samples? So does order matter here? No. So is that a permutation or a combination? It's a combination. That's correct. So you'd use the NCR formula. And then 19 was 11 groups entered a science fair competition. And how many ways can the groups finish first, second, and third? So is that a permutation or a combination? Permutation, because order matters because we have first, second, and third place. So it would be 11 P3, right? And then you were supposed to solve them. Any questions about Friday's work? So 1, 2, and 3, and 4 are from our assignment from Monday. So you will work that on your study guide. 1, 2, 3, and 4, that was your bell work today. And we'll go over these later. Okay, now let's look at today's work. All right, so everybody pass forward 11-2, all right, or 11-1, excuse me. You've got 11-2 on your desk. All right, make sure you put your name and your hour on your study guide now on the cream colored paper, or yellow, orange, whatever, gold. We'll call it gold because you're golden. Meh. All right, so today we're going to talk about experimental probability. So this is 11-2. All about probability. But the first thing we're going to talk about is experimental probability. And with this lesson on our study guide, you'll be working 1, 3, and 5. Now, you'll do that for bell work tomorrow, but if you want to work it tonight after you finish the assignment, those are the ones. And it's on the back. Okay? And these are what's on the test. All right, so for experimental probability, it says probability just measures how likely something is to occur, or an event. An event could be how many green marbles can you pick from the bag? Right. How many cars or how many boats are in the parking lot as opposed to cars, right? Those are events. How likely is something to happen? So the probability of an impossible event is 0. So if I say there is 0% chance that that is likely to occur, it means it's not going to happen. So if it's raining outside, we say, well, there is a 100% chance of rain. 100% means it's happening. It's happening right now. It's totally going to happen. Okay, so from 0% means not likely at all to 100% means it's going to happen. You will also see this as 0 and 1. And then everything in between are the chances of the probability that it might happen. Okay, so if I say there's a 40% chance of rain today, well, that's falling closer to not going to happen than going to happen, right? But there's still a pretty good chance. At 40, you're not quite at 50. So these are things that we're going to talk about today. Now, how do you figure out your experimental probability? Well, we're going to say you're going to look at what do you want, or the number of times an event occurs. Event occurs, I'll just abbreviate there, over the number of trials. So let's look at how to use this, and it's going to be a capital P of the event, whatever that event is. How many times did it occur over how many times did you try? All right? So here's an example of putting that to use. Of 60 vehicles in the teacher's parking lot today, there are 15 pickup trucks. What is the experimental probability that a vehicle in the lot is a pickup truck. So again, we're going to say, well, the event is how many are pickup trucks? So P of pickup trucks, I'm going to abbreviate, is equal to, okay, how many were there? 15 over how many total vehicles? 60. So your event over the total number. So there it is. P of pickup truck is equal to number of pickup trucks over the number of vehicles, which was 15 over 60, which is 0.25 or 25%. So you'll see it all these ways. So on a test, before you start simplifying, you just might look at your answer choices before you start turning it into a percentage. Because it could be in decimal form, or fraction form. So you'll say the probability that the vehicle in the lot is a pickup is 25% or 0.25. Any questions over that? Okay, look at number 1 on your work, on your homework practice K. Yeah, just put your study guide away. We're not going to do any of the study guide in class. So a baseball player got a hit in 12 of his last 40 at-bats. What is the probability that he will get a hit at his next bat? So the probability that he gets a hit at his next bat is equal to, what's the favorable? How many did he get? 12. Over how many total? 40. So that simplifies to, so 6/20 or 3/10. And what is 3/10? So about 30%, right? 3 out of 10 is 30%, or 0.3. Any questions on that? Okay, so tonight you will work 2 and 3 by yourself, okay? And if we have time, we'll come back to them, okay? So mark out the rest of this page, scribble through 4 and X through 5, 6, 7. We're not doing those. All right, so now we're going to talk about what is a sample space. A sample space would be like, did anyone ever practice ball on a pitchback thing? It's like a little net that you bounce a ball into and it bounces it back to you. Well, there's a sweet spot on that net that you're always aiming for, so it'll pitch back the prettiest angles for you to catch. Well, these are the kind of things that you need to think about when we're talking about sample space, right? So let's use this for an example. Let's say if I have that pitch back and I say, okay, this is, let's make it a giant one. Let's say it is 10 feet by 8 feet, right? And that sweet spot in there is going to be 3 by 2. So what's the probability if we throw a ball at that and hit on the net? What's the probability that we're going to hit in the sweet spot? So we would say the probability of the sweet spot is equal to, well, 10 times 8, 80 total. But what's at sweet spot? 3 times 2. So we have a 6 in 80 chance of hitting that sweet spot. Okay, so that's sample space, is when we're talking about geographic space. Any questions on that? All right, let's look at their examples. Now they're going to talk about rolling a standard dice. So here's another example for sample space. So now they're talking about a 3D object. You've got a standard dice. They call it a number cube. They also call it a fair number dice or something later on, but just remember you're rolling like what you play in games. It has 6 sides, 1 through 6, dots on it. So for one roll of a standard number cube, there are 6 equally likely outcomes in the sample space. So for a sample space, it has to be equally likely, right? So they're all the same size. So we have the same chance of hitting any of those, right? So we can calculate the theoretical probability as a ratio of outcomes. So let's look at our first problem. If a sample space has n equally likely outcomes and event A occurs in m of these outcomes, then theoretical probability of the event A is P of A is equal to m over n, right? So there's that sweet spot. There's the whole pitch back, right? So it was m divided by all of it. Okay, so what is the theoretical probability of each event? A says getting a 5 on one roll of a standard number cube. So getting a 5, well, we know there's 6 likely outcomes, but 5 is just one of those, right? So if we roll that dice one time, we have a 1 out of 6 chance of getting that 5. Everybody see that? Any questions about that? Okay, now let's make it just a teeny bit harder. Now it says getting the sum of 5 on one roll of 2 standard number cubes. So now we're going to roll 2 dice, and we got to get the sum of 5. So how many ways can we get a 5 if we roll 2 dice? So we can get a 2 and a 3, or a 3 and a 2, and what else? 1 and a 4, or a 4 and a 1. So we can get it 1, 2, 3, 4 ways, right? And what's possible? We've got 6 sides here and 6 sides there. So 6 times 6 is... So 36 possible, but there's only 4 ways to get that. So out of 36 chances, we have 4 chances of getting a sum of 5. So it's going to be 4 out of 36. So there it is. There's our possibilities that you just talked about. Good job. So the probability of getting the sum of 5 on the 2 dice is 4 ways out of 36 possible ways, which is 1/9. So 1 in 9 chance. So if I roll those dice, and I wish I had dice to give you guys today to play on these and see what your chances are. Does the statistics hold up? So if I've got a 1 in 9 chance of getting a sum of 5. So if I roll that dice 9 times, out of that 9 times, I should at least have a sum of 5 once. Okay? Any questions on that? All right, let's look at our workbook on the back. Let's look at 8 and 9. There it is, fair number cube. Okay, just a standard dice is what that is. Your classmate rolls a fair number cube. What's the theoretical probability that she will roll a number greater than 4? So let's look. We know we've got 1, 2, 3, 4, 5, 6. Those are our possibilities on this one dice. And they want to know what's the chance that we're going to roll a number greater than 4. Well, how many of these numbers are greater than 4? 2. So she has a 2 in 6 chance. So probability of a 4 is equal to 2 out of 6, or simplify, a 1 in 3 chance of getting a number greater than 4. So if we roll the dice 6 times, we should see at least twice that we would get a number greater than 4. Or if we roll the dice 3 times, we hope at least once we'll see that a number is greater than 4. And that's just predicting, right? It's possible that you could roll it 3 times and never get it, but on an average, if you kept doing it over and over and over, that's your chances. Okay, any questions on that? All right, let's look at the next one, and then you'll do 10 on your own at home. Number 9 says Sean rolls a pair of fair number cubes, so she's going to roll 2 dice now. So let's forget this one. I'm going to use this. So she's going to roll 2 dice. What is the theoretical probability that he will roll a sum of 3? So how many ways can we get a 3? 2 and 1, and we can get a 1 and 2, and that's it, right? So we have 2 ways. Out of how many when we have the 2 dice? What was that number we used? 36. So the probability of sum of 3 is equal to 2 chances out of 36 possibilities, which is 1/18. And if you want to take that down any further, that's equal to 0.0555556, which is, we can round that up to about 6%. Okay, so lots of ways to represent that. That's a percent, by the way. So 6% chance. Any questions? If you like this, you can make really good money working for an insurance company predicting what people are going to do in their life and how much insurance to charge based on those odds. And they make like doctor money, like 150 grand is what Mr. Dunning said. He's got a friend who does that. And they just got a math degree in college and make like 150 grand a year. It's like, are you kidding me? I never knew that. So you'll work number 10 at home. Now this one, let me give you food for thought on it. A box contains 24 green markers. So 24 green, 16 red, and 10 blue. So your total for all these is going to be this plus this plus this, right? That's your total. And then they want to know, well, what's the probability that you're going to get red marker, green or blue, or not green? So that's what you're going to do on number 10, and then you'll turn that in tomorrow. Let's mark out number 11 on your workbook, and then we're going to work on our last problem. You might get some class time. Here's that sweet spot thing I was talking about. So a batter strike zone, and this is geometric probability. A batter strike zone depends on the height and stance of the batter. What is the geometric probability that a baseball thrown at random within the batter strike zone, as shown in figure below, will be a high inside strike, which is one of the hardest pitches to hit? So lots of words, but they're saying here is in this yellow box, here's the strike zone. Here's the sweet spot right up there, that little red box in the corner that I scribbled over. What's the chance that in this strike zone he will hit that little red box? Well, they give us some dimensions. So let's go, well, the probability of the strike zone, or what they call it, high inside strike area. So probability of high strike area, I'm just going to call that HSA, is equal to, now what's the total distance is 22 times 17. So let's go 22 times 17, and that is 374. And then our sweet spot here is 4 by 6. So what do we want? What's our desired hit zone? Is 6 times 4, which is 24. Now let's simplify that. 24 divided by 374 is equal to 0.0641711123. So we want to take that to about right there, so it's about 6%. He's got a 6% chance of hitting that sweet spot in that strike zone area. Okay? Any questions on that? So it's always, what do you want over what's possible? What do we want? That sweet zone. What's possible? This whole big zone. Or the favorable over the total. Favorable is what do you want? Total is what all's there. Any questions? Excuse me. All right, let's look at our workbook again, number 12. It says, use the area to find the following theoretical probabilities. So again, this is a geometric probability. The floor in your friend's house covers 1,400 square feet. So the whole floor is 1,400 square feet. The floor in her bedroom is 14 by 10. When that makes it 14 times 10 is 140. So 140 square feet. What is the probability that a randomly selected point on the floor in the house is in your friend's bedroom? So probability of hitting a point in the bedroom is, okay, what do we want? The bedroom, that 140. What's possible? The whole room, 1,400. So what's the chance here? We'll simplify. Take your 0 off, and 14 goes into 14-1. So it's a 1 in 10 chance, which is 10% chance. Everybody with me? Any questions? That's everything, guys. You're so quiet today. You'll work 13 at home. So in all, you're going to work 1, 2, and 3, 8, 9, 10, 12, and 13. And we've already worked most of those. So see if you can finish that up real quick. And then tomorrow for bell work, we'll do the study guide associated with this lesson, which is numbers, and it's on the back. 11-2 is 5, 6, and 7. They're going to be just like these. Okay? All right, this concludes our lesson. Thank you.